In this lecture, we're going to prove that a general equation of degree 5 is not solvable in radicals. A major theorem that we're going to prove in the course of the next lectures states that a Galois extension of Q is radical if and only if its Galois group is solvable. Today we're going to prove one half of this theorem. So we're going to prove the following claim, that let E be a radical Galois extension of Q then the Galois group of this extension is solvable. And then we're going to construct an explicit irreducible polynomial of degree 5 whose splitting field has a non-solvable Galois group. First, let us recall the construction of a radical extension. So we say that the extension E is radical if there exists a chain of field extensions of Q. So Q, which is E0, which sits in E1, which sits in En, and E is a subfield in En, such that for every k from 1 to n, there exists an element alpha k in Ek and an integer mk such that Ek is equal to Ek minus 1 with a joint alpha k, and alpha k to the power mk belongs to Ek minus 1. Our first remark is that we may assume that this top extension En is a Galois extension of Q. To prove this, we consider possible embeddings sigma of En into Q bar. We point out that each such sigma induces a similar chain. So we will have Q, which sits inside sigma of E1, which sits inside sigma of E2, and this sits in sigma of En. Let sigma 1 through sigma s be all such embeddings. Then we construct the normal closure of En as the product sigma 1 of En times sigma 2 of En times sigma s of En. This will be a subfield inside Q bar. Let us call this field E tilde. Then, for an embedding mu of E tilde inside Q bar, so we can see that mu will permute the fields sigma I of En. And from here we conclude that mu of E tilde is equal to E tilde. This implies that E tilde is normal over Q. So thus this extension is Galois. So here we are in characteristic 0, so every extension is separable. And we can put all these chains together to form one big chain for E tilde. So we will have that Q, which is E tilde 0, sits inside E tilde 1, and so on, sits inside E tilde n times S, which is our field E tilde. And all these extensions are radical in the sense that at each step we join one mth root. And then in this chain we can replace En with E tilde, and then we can just assume that En is already a Galois extension of Q. In our last lecture we proved that in the statement of our main result we are allowed to replace the field of rational numbers with a cyclotomic field. Now, the question is, which cyclotomic field should we choose? The order of the root of unity that we are going to adjoin is determined by the exponents mk's. Let capital N be the least common multiple of the exponents m1 through mn. Then we fix zeta to be e to the 2 pi I over capital N, so this is the nth root of 1, and we fix k to be q extended with zeta, so this cyclotomic field that corresponds to this nth root of 1. As we saw in our previous lecture, it is sufficient to prove the following modification of this theorem. So theorem with a prime. Let E be a radical Galois extension then the Galois group of Ke over K is solvable. What we are going to do is we can multiply each term in this chain by the cyclotomic field K. And then we will get that K, which is K E0, sits inside K E1, and so on, will sit inside K En. Still, each step of this extension is obtained by adjoining one mth root. So what we're going to do is we're going to change notations and just denote k times ej by simply ej, just to simplify notations. And then we're going to get this chain, but it will start not with q, but with k. So we will have that k is E0, will sit inside E1, and inside En. And we will have that En is normal over K. Since Ke is normal over K, this tells us that the Galois group of En over Ke is a normal subgroup in the Galois group of En over K. And the Galois group of Ke over K is isomorphic to the Galois group of En over K, quotient by the Galois group of En over Ke. Now we see that it is sufficient to prove that the Galois group of En over K is solvable, since a quotient of a solvable group is again solvable. So if we can prove that the Galois group of En over K is solvable, then we conclude that the Galois group of Ke over K is solvable. And that's exactly what we need. Next, let us analyze a single step in this chain of extensions. We have the following lemma. Suppose F contains a primitive mth root of 1, zeta. So this means that zeta to the power m is equal to 1, and the set 1 zeta, zeta squared, up to zeta to the power m minus 1. So these elements are all distinct. And let E be f with a joint element alpha, such that alpha to the power m, which is beta, belongs to f. Then the extension of f to E is Galois, and the Galois group of E over f is a subgroup in the additive group Zm, and hence abelian. To prove this lemma, we point out that E is a splitting field of a polynomial x to the power m minus beta, since this polynomial factors as x minus alpha times x minus alpha times zeta times x minus alpha zeta squared times x minus alpha zeta to the m minus 1. And we see that the field E will contain m distinct roots of this polynomial. Since E is a splitting field, we conclude that the extension f to E is Galois. Let us try to understand the structure of this Galois group. So let sigma be an element in the Galois group of E over f. Since E is generated by a single element alpha, this automorphism is determined by its value sigma of alpha. And this automorphism will permute the roots of this polynomial. So this tells us that sigma is determined by its value sigma of alpha, and this value must be alpha times zeta to some power a. We have that zeta belongs to f, and sigma restricted to f is identity. From here, we conclude that for each k, sigma of alpha zeta to the power k is equal to alpha zeta to the k plus a. If we have another automorphism mu, then mu of alpha will be alpha times zeta to the power b. Let us see what will be the composition of sigma and mu. So we will have that mu of sigma of alpha is equal to mu of alpha zeta to the power a, and this will be alpha zeta to the a plus b. From here, we see that to each automorphism we can associate a remainder mod m, and the induced group structure on the set of remainders is additive. So this tells us that the Galois group of E over f is a subgroup inside the additive group of Zm. We cannot claim equality here because in general, not for every A there will be a corresponding automorphism. Now let us consider our chain where we adjoin radicals. So we have K, which is E0, sits inside E1, sits inside E2, and so on up to En. We make the following claim, that for all j from 0 to n, the Galois group of En over Ej is solvable. We're going to prove this by reverse induction in J. So the basis of induction is the case when J is equal to n. And this case is trivial because the Galois group of En over En is the identity. Now let us do the step of induction. So we assume that the Galois group of En over Ej plus 1 is solvable. We have that Ej plus 1 is the extension of Ej with adjoining element alpha j plus 1, with alpha j plus 1 to the power mj plus 1 belonging to the field Ej. By the construction of K contains a primitive root of 1 zeta of degree mj plus 1. And this implies that this zeta also belongs to Ej. And then by lemma that we proved, the extension Ej plus 1 of Ej is normal, and the Galois group of Ej plus 1 over Ej is cyclic, since a subgroup of a cyclic group is cyclic. This tells us that the Galois group of En over Ej plus 1 is normal in the Galois group of En over Ej, and the quotient, so the Galois group of En by Ej quotient by the Galois group of En by Ej plus 1 is isomorphic to the Galois group of Ej plus 1 by Ej. This tells us that the Galois group of En by Ej has a solvable normal subgroup with a solvable quotient, which is even cyclic. And this implies that this Galois group of En by Ej is itself solvable. And this proves the induction step. So we assume that the Galois group of En over Ej plus 1 is solvable, and we prove that the Galois group of En over Ej is solvable. Now, if we set j to be 0 in our claim, then we get the statement of our theorem. So we conclude that the Galois group of En over K is solvable. So we proved that if E is a radical Galois extension of Q, then the Galois group of E over Q is solvable. The contrapositive to this is that if the Galois group of E is not solvable, then E is not radical. Now, why is this that we have formulas for solutions of equations of degree 2, 3, and 4, but not to equations of degree 5 and higher? So it turns out that the answer is given by group theory, that if we take permutation groups S2, S3, and S4, these symmetric groups are solvable. And if we take Sn, where n is greater or equal to 5, these groups are not solvable. So the first symmetric group that's not solvable is S5. And indeed, if we take S5 and take its commutator subgroup, then the result will be A5, the alternating group, so the symmetric permutations on 5 letters. But the group A5 is simple and non-abelian. So this means that it has no non-trivial normal subgroups. And the commutator subgroup is normal. So because A5 is non-abelian, this implies that the commutator subgroup of A5 is different from identity. And because it's simple, this implies that the commutator subgroup of A5 is itself. But then, for all k, the kth commutator subgroup by induction of A5 is A5. So this tells us that the chain of commutator subgroups of S5 does not descend to identity. And this tells us that S5 is not solvable. And since S5 is a subgroup inside all Sn with n is greater or equal to 5, so this implies that Sn with n is greater or equal to 5 are not solvable, because we know that a subgroup of a solvable group is solvable. This implies that these Sns cannot possibly be solvable groups. Next, let us produce an example of a polynomial f in Q of x of degree 5, such that the Galois group of the splitting field of this polynomial is isomorphic to S5. Since S5 is not a solvable group, this tells us that the roots of f are not expressible in radicals. Let's consider a polynomial f of x is equal to x to the power of 5 plus 2x cubed minus 6x plus 2. First of all, we know that this polynomial is irreducible by Eisenstein with p equals 2. Let us show that the Galois group of this polynomial is S5. We begin by determining the number of real roots of this polynomial. We state the following lemma. Let G belong to R of x. Then real roots of G are interlaced by the roots of the derivative G prime. More precisely, if g of A and g of B are equal to 0, where A is less than B, then there exists a real number C, which is in between A and B, such that g prime of C is equal to 0. This is a well-known lemma in calculus, that if we have a smooth function with vanishes at A and B, then there is an extremum point in between where the derivative is equal to 0. As a corollary, we get that if g prime has k distinct real roots, then g has at most k plus 1 distinct real roots. Now let us look at the third derivative of our polynomial. So the third derivative of this polynomial is going to be 5 times 4 times 3. That's 60x squared plus 12. And we see that this expression is strictly positive for all real x. So this tells us that the third derivative of our polynomial has no real roots. And then by lemma, we get that the second derivative has at most one real root. Then the first derivative has at most two real roots. And our polynomial itself has at most three distinct real roots. Now let us compute some values of this polynomial. What is f of minus 1? So this is minus 1, minus 2, plus 6, plus 2. So this is equal to 5. And f evaluated at 1 is equal to 1 plus 2 minus 6 plus 2. That's negative 1. We also know that the limit when x goes to minus infinity of this polynomial is equal to minus infinity, and the limit when x goes to plus infinity of this polynomial is equal to plus infinity. This tells us that f has a root on the interval from minus infinity to minus 1, then it has a root on the interval from minus 1 to 1, and it has a root on the interval from 1 to plus infinity. Since this polynomial switches sign on each of these intervals. This tells us that our polynomial has precisely three distinct real roots. And our polynomial is irreducible. And this implies that f has no multiple roots. Otherwise, it will have a non-trivial greatest common divisor with its derivative. So we conclude that f has three real roots and a conjugate pair of complex roots. Since the coefficients of f are real, its complex roots always come in conjugate pairs. Indeed, so if we have that f of z0 is equal to 0, then taking the complex conjugation will obtain that f of z0 bar is also equal to 0. Now let us consider the Galois group. So let E be the splitting field of this polynomial. So that is, we join to rational numbers all 5 roots of this polynomial. And let G be the Galois group of E over Q. We know that this Galois group acts by permutations on the set of roots. So this tells us that this group is a subgroup inside S5. And we know that this subgroup is transitive. And thus, the order of G is divisible by 5. Since G has an orbit of length 5, and the length of an orbit is a divisor of the order of a group. Since order of G is divisible by 5, and the order of S5 is not divisible by 25, this implies that the Sylow 5 subgroup in G is isomorphic to Z5, and thus G contains a 5 cycle, because 5 cycles are the only elements of order 5 in S5. Let's denote this 5 cycle by sigma. Since F has a pair of conjugate complex roots, we conclude that the Galois group contains complex conjugation. Complex conjugation will become an automorphism of the splitting field that will swap 2 complex roots. As a permutation, this automorphism is a transposition. So we say that G contains a transposition tau. If we label our complex roots as 1 and 2, then tau as a permutation will be written as a transposition 1, 2. Since sigma is a 5 cycle, there exists a power of sigma. So there exists j, such that sigma to the power of j will send 1 to 2. Let us fix this j, and let's denote sigma to the power of j as mu. Then mu is a 5 cycle, and as a 5 cycle it will start with 1 and 2, and then we can label the 3 remaining roots such that mu is 1, 2, 3, 4, 5. We claim that permutations 1, 2 and a cycle 1, 2, 3, 4, 5 generate S5. There is the following useful fact about permutations, that if tau sends element A to element B, then eta tau eta inverse sends eta of A to eta of B. Indeed, eta inverse will send eta of A to A, then tau will send A to B, and finally eta will send B to eta of B. So this composition sends eta of A to eta of B. So if we take this transposition tau and this 5 cycle mu, then mu tau times mu inverse will be a transposition that swaps mu of 1 with mu of 2. So that will be a transposition 2, 3. Then if we take mu squared tau mu to the negative 2, this will be a transposition 3, 4. And finally, if we take mu cubed tau mu to the negative 3, this will be a transposition 4, 5. So we obtain that the subgroup generated by mu and tau contains the elements 1, 2, 2, 3, 3, 4, and 4, 5. But we know that adjacent transpositions generate the whole group S5. And we conclude that the Galois group of this polynomial is equal to S5, which is not solvable. And this means that the equation x to the power of 5 plus 2x cubed minus 6x plus 2 equals 0 is not solvable in radicals.